In this demo, we will be measuring a 1.634-inch or 41.5 millimeter sample of thick fiberglass. We will be using an Olympus 38DL Plus thickness gauge. The exact key presses would be different if you were using a different model Olympus thickness gauge, but the overall process would be the same. Normally, for this application, we would use a lower frequency transducer, like the 0.5 MHz M2008, but for training purposes, we are going to use the 2.25 MHz M1036 transducer. The first step would be to connect the transducer and plug the transducer cable into TR1 at the top of the instrument, then turn the instrument on. Once the instrument is on, press the XDCR recall key. If we were using a transducer with a frequency lower than 2.25 MHz, we would need the HP software option and would choose default HP single element. However, since we are using a 2.25 MHz transducer, we will press the down arrow to default single element and then press Enter. Here you will see the list of default single element transducer setups. Press the down arrow to highlight DEFM1-2.25-M1036. At this point, you can press the red measure key to recall the setup, or press the Enter key to see the parameters within the setup. If you press Enter, press the red measure key next in order to recall the setup and return to the measurement screen. The default setup we recalled has a default sound velocity for stainless steel, so we need to change it to something closer to fiberglass. To do this, press and release the second F key first, and then press the Cal-Vel key. The stainless steel velocity is 0.2260 inches per microsecond, or if you are using metric units, it will be 5.740 millimeters per microsecond. Use the arrow keys to change this value to the approximate sound velocity for fiberglass, which is 0.108 inches per microsecond, or if you are using metric units, it will be 2.743 millimeters per microsecond. Then press the red measure key. Next, we will need to change our range. Currently, the range is set to 0.5 inch. If you are using metric units, it will be set to 10 millimeters. Given the thickness of our sample, we will not be able to see the back wall on screen since the range is currently set too low. To change the range, keep pressing the blue range key until the bottom right side of the screen displays 3.00. If you are using metric units, it will be set to 50.0. Now, since we changed the velocity to be close to fiberglass and we adjusted our range appropriately, we now have a rough idea of where the back wall echo should appear. Given the thickness of the part, the back wall echo should appear to the right of the center of the screen. We can now apply couplant to the part and couple the transducer onto the sample. We start to get a reading. However, it does not appear to be correct. The signals being detected appear too soon in time to represent a signal from the back wall, and thus are likely reflections from the internal fibers within the sample. You can attempt to locate the back wall echo by adding couplant to your finger and touching the back side of the sample opposite the transducer. The true back wall echo would be dampened slightly by your finger, while the internal reflections would be unaffected. This can be seen from the signal circled in red. In order to detect the true back wall echo, we need to make some internal adjustments to gain. To do this, press the Wave Adjust key. This will bring up the setup parameters at the bottom of the screen. Press the down arrow to the gain settings. Once you get to max gain, you will see the yellow gain line which identifies which of the 3 gain settings need adjustment. Press the down arrow to INIT gain, then use the left arrow to lower the initial gain slightly to reduce internal reflections appearing sooner in time. Since the majority of internal reflections are under the slanted portion of the gain line, we need to lower the TDG slope. Press the down arrow to TDG slope, then use the left arrow to lower the slope until the gauge stops detecting the internal reflections and instead detects the true back wall echo. Lastly, we will make a slight adjustment to the max gain. Press the up arrow twice to max gain, then use the right arrow to increase the max gain slightly to further amplify the true back wall echo. The gauge is now detecting the true back wall echo, and the signal is strong in amplitude. At this point, it is a good idea to check multiple spots on the sample to make sure no further adjustments are needed. If you can successfully measure the back wall echo on multiple spots on the sample, then no further adjustments are needed, and we can go ahead and calibrate. For best accuracy, we would calibrate using 2 samples of the same material with known thicknesses representing our minimum and maximum thickness. For this demo, we only have 1 sample, so we will perform a single-point velocity calibration. To do this, we will first press the yellow Cal-Vel key and then couple onto the sample. Once you have a steady reading, press the Enter key. Then use the arrow keys to change the value to 1.634 inches or 41.5 millimeters. Then press the red measure key. You'll notice variations in thickness when measuring from point to point on the same sample. This was discussed in previous slides and is caused by variations in the ratio of fiber to resin within the sample, which in turn causes changes in the time of flight measurement and thus the thickness reading.